We are going to be talking about the Laplace transform of derivatives and the derivative of the Laplace transform. And we will use a few applications for that topic. It is a continuation of chapter 7 that we are working, which are all tools that are used to solve differential equations, linear differential equations with fixed coefficients. I gave you an example at the end of the last lecture of a problem that can be completely solved using the Laplace transforms. So in here, the first part is Laplace transform of a derivative. So the Laplace transform of f prime of t is equal to s times the Laplace transform of f of t minus f of 0. This is the theorem that we will be using in this part. It is easy to prove this using integration by parts. Uses the definition and integration by parts. So we are not spending class time on that. The problem for us will be how to use these things. Okay. An example will be, let's say we have the function f of t equals integral from 0 to t of g of t of g of, let's say, g of tau d tau, making sure that the variable of integration is not the variable that you have there. So notice that the derivative of f is equal to g of t, right? The derivative of the integral with respect to the upper bound is equal to the value of the function at the upper bound here, that is t. So, and moreover, what is f of 0? What's f of 0 in this case?
Wouldn't it be 0?
That's 0. Integral from 0 to 0 is 0, no matter what is the function that is inside. So, that being said, if we are using this theorem, we would say Laplace transform of f prime of t equals s Laplace transform of f of t minus f of 0. F prime of t is g of t. So Laplace transform of g of t equals s. F of t is the integral 0 to t g of tau e tau And this tells you that the Laplace transform of the integral from 0 to t of g of tau d tau equals 1 over s Laplace transform of g of t. So using the Laplace transform of a derivative, we are able to establish that the Laplace transform of the integral is equal to 1 over s times the Laplace transform of the function, no matter what that function is. This needs to be known. The same as that needs to be known. So example, find the Laplace transform of integral from 0 to t of cosine of tau e to the 2 tau d tau. If I ask you to find this, it would tell me that that is equal to 1 over s times the Laplace transform of cosine t e to the 2t. And so, that being the case, now you just need to find the Laplace transform of cosine t e to the 2t. Who wants to help me here? How do I find the Laplace transform of cosine t e to the 2t? Anyone to help me here?
Is that something to do with the first translation theorem?
It's up to you. You choose what to use.
Wouldn't we take the Laplace transform of cosine of t and then substitute s minus 2 instead of s?
And that is the translation theorem. And what is the Laplace transform of cosine t?
S over s squared plus a squared.
Correct. And 1. And then in this one, you replace s by s minus 2. Not the whole thing, but just this part. And that's why you get 1 over s times s minus 2 over s minus 2 squared plus 1, which is s minus 2 over s times s squared minus 4s plus 5. That's it. With a given definition in the theorem, how would we find the Laplace transform of the second derivative of a function? We would say it is s times the Laplace transform of the first derivative minus the value of the first derivative as 0. That is because the second derivative is the derivative of the first derivative. And we know that the Laplace transform of the derivative is also s Laplace transform of y minus y of 0, then minus y prime of 0. So technically, you can say Laplace transform of the second derivative is s squared Laplace transform of y minus sy of 0 minus y prime of 0. And you can do this as many times as you want. You can find Laplace transform of third derivative, fourth derivative, fifth derivative consecutively without any issues. So Laplace transform of the third derivative is s Laplace transform of the second minus the value of the second derivative as 0. And that is s, and the Laplace transform of the second derivative is that. So that's s squared Laplace transform of y minus sy of 0 minus y prime of 0 minus y double prime of 0. And that is equal to s cubed Laplace transform of y minus s squared y of 0 minus s y prime of 0 minus the second derivative at 0. So that's for the third. And you can continue fourth, fifth, sixth, and so on. This is mostly used in the applications when you want to solve the differential equation or the integral differential equation. You get things like that show up, and then you can solve. So that's it for the Laplace transform of the derivative. The other thing is the derivative of the Laplace transform. That's the second part of this. And here I always give the simple form, which also you can obtain by integration, doing integration by parts. The Laplace transform of t, f of t, is equal to negative derivative with respect to s of the Laplace transform of f of t. Or derivative with respect to s of the Laplace transform of f of t equals negative Laplace transform of t, f of t. One can also say that t, f of t equals negative inverse Laplace transform of d over ds of Laplace transform of f of t. This is another way you can use it. So there are three different ways you can write this down and use. So in most of the problems, often this is the most important, but forward, that's how you use it. So examples. One is Laplace transform of t cosine of 2t, for example. If I want to find this, then this theorem tells me that's t cosine, so it's negative derivative with respect to s of the Laplace transform of cosine 2t, which is negative derivative with respect to s, and the Laplace transform of cosine 2t is s over s squared plus 4. And you need to take that derivative, and this is equal to negative. That's a ratio, so quotient rule. So that's going to be s squared plus 4 minus 2s squared over s squared plus 4 squared. And this is equal to s squared minus 4 over s squared plus 4 squared. And that's how you get the Laplace transform of t cosine 2t. Notice that if you don't have this theorem, it'll take you a lot of time to figure out what the correct answer to this problem is. Any questions? Now you find me the Laplace transform of t sine hyperbolic of 3t because is equal. That's a theorem. That's an example. Can you do this? So who can present his answer? What's the first step?
It'd be negative d over ds and times the Laplace transform of hyperbolic sine of 3t.
Okay, that's the next.
It would be negative d over ds, and then the Laplace transform of hyperbolic sine of 3t would be 3 over s squared minus 9.
Correct. And then
And then use the quotient rule again. So to take the derivative, so it'd be negative times negative 6 over s squared minus 9 squared. So then it would just be 6s over s squared minus 9 squared.
that's it. That's correct. That's what we do. That's how the procedure works. And that is how you use it forward. You use here forward to find the Laplace transform when you have a t. Now another example. In this second example, you want to do that twice because you got a t squared. So how do we find Laplace transform of t squared? Sine of t. Let's go on the first step, Preston. What do we get?
Would that make it the second derivative or just
We go one step at a time. T squared is t times something times t.
so would it be the negative second derivative of s?
I can give any formula that involves second derivative. So every time you see t, it's negative d over ds of whatever remains.
So is it negative derivative of ds? Okay.
Now in your second step, you want to find this, and that's again t times something. So that's another negative d over ds. Laplace transform of sine t. So technically that gives you second derivative. And the Laplace transform of sine t, what is it? Michael?
It's going to be 1 over s squared plus 1.
All right. And then you're going to take twice the derivative. So that's derivative with respect to s. And this is minus 2s over s squared plus 1 squared. Then you take that derivative and get minus 2 s squared plus 1 squared minus, and then the minus 2 is plus 2s times the derivative of the denominator, which is 2 times 2s, that's 4s times s squared plus 1. divided by s squared plus 1 squared squared, which is to the power of 4. And that gives you, you can divide, cancel one of the s squared plus 1, so you get negative 2 s squared minus 2 plus 8 s squared over s squared plus 1 to the power 3. And that gives you 6s squared minus 2 over s squared plus 1 cubed. That's how you would find the Laplace transform of t squared sine of t. Now, how do we use this one backwards? Backwards is when you want to find the inverse Laplace transform. When you want to find the inverse Laplace transform, you use the formula backwards. Find so we say find the inverse Laplace transform of natural log of s squared minus 4 over s squared minus 9. And if you're not in this class now, you say game over. Because first of all, you see natural logs. Why do you have natural logs there? No idea, right? And there is none of the functions that we have used that involves natural log. So to get rid of this, you must think of using the derivatives of Laplace transforms. Like we said, t f of t equals negative inverse Laplace transform of d over ds Laplace transform of f of t. So if I want to find the function f of t that turns into this, again, listen carefully. If I want to find a function that turns into this, that's f of t, then I can take the derivative of this function. That will be what goes inside this formula here. And therefore, if I find the inverse Laplace transform of that and multiply by minus 1, it's going to be t times f of t, which is the function I'm looking for here. That's how you apply backwards the Laplace transform of the derivative, or the derivative of the Laplace transform, sorry. So here, what is going to happen is we are going to split this thing, natural log of s squared minus 4 over s squared minus 9. It's natural log of s squared minus 4 minus natural log of s squared minus 9. And I'm going to take the derivative of each of them in this formula. So that's going to be negative inverse Laplace transform of derivative of d over ds natural log of s squared minus 4 minus d over ds natural log of s squared minus 9. So that's negative inverse Laplace transform of, and this derivative is 2s over s squared minus 4, and that one is 2s over s squared minus 9. Now this gives me negative 2 inverse Laplace transform of s over s squared minus 4 plus 2 inverse Laplace transform of s over s squared minus 9. And you need to know what you are doing on each of the steps, not just taking the functions up and down, right? That's a derivative. I'm taking derivatives. I compute those derivatives. I get this. And then I simplify. And now, what is the inverse Laplace transform of s over s squared minus 4?
Is it hyperbolic cosine of 2t?
That's correct. So that's minus 2 hyperbolic cosine of 2t plus 2, and this one is?
Hyperbolic cosine of 3t.
That's right. And so that is tf of t, which leads to f of t equals negative 2 over t cosine hyperbolic of 2t plus 2 over t cosine hyperbolic of 3t. So this is the thing. That's how you use it. Any questions? Was there a holiday today?
No, but there's a holiday tomorrow.
Because I have only half of the class. That's why I'm asking. So people didn't show up. I thought maybe they are celebrating something today. It might be if you send me a private email that I didn't reply to, just need to know it's not because I don't want. I actually got involved in a hit and run on my way back from the airport on Saturday. So I just got out of the hospital yesterday. Things have been very rough for me lately since we started this class. I have no idea why, but everything is just falling like that. Now, let's do a second example here. And this time I'm asking you guys to work this one out. You find the inverse Laplace transform of let's say arctangent of S. Well, what will you do here? That's 1 over S, okay? Not S, just. Yeah, tell me what's the first step. So you want to try me? Tell me they're here, Messi.
Me?
Yep.
Okay, you would start off by saying f of t is equal to negative inverse Laplace transform of d over ds times the Laplace transform of arctan of 1 over s. Is that right?
Just this, just this is the Laplace transform already.
And then isn't the derivative of arctan 1 over x squared plus 1? So here it would be 1 over s squared plus 1. Is that right?
There's something else. It's negative first. Let's go step by step. How do you take the derivative of a function that sits inside another?
So it would be negative 1 over s squared times 1 over s squared, like 1 over s quantity squared plus 1. Okay.
This is what you will get. Negative 1 over s squared, because you're taking first derivative of 1 over s, which is negative 1 over s squared, times chain rule, derivative of arctangent, it's 1 over 1 plus x squared, and you replace that by 1 over s. And you find the common denominator, and you find out that all this is equal to 1 over s squared plus 1. Do you agree with me? Beautiful. And then all you need now is to find the inverse Laplace transform of this. What is it equal to? What's the inverse Laplace transform of 1 over s squared plus 1?
Isn't it sine t?
Sine t. That's it. So what you get is t, f of t equals that. So f of t is 1 over t sine t. So this is the function that has Laplace transform that. Any questions? Hello, ask me any questions. No? Okay, let me ask you one if you don't. Find the inverse Laplace transform of how can we do this one? Cotangent minus 1 of s 2s minus natural log of s plus 1. Take your time, work it out, and tell me what you get. Same steps as the other one. Just that you need to figure the derivative of cotangent minus 1. All right, who wants to share with us? Michael?
No, thank you.
There are two Michael. I know, Hill. I'm talking about Michael Payne. Charlie?
I'm not too sure on this one.
Cooper?
Did you say my name? I'm sorry, my internet connection is unstable.
Get it. So yes, I was asking if you could share your thoughts on this one.
I'm having a lot of trouble solving this one.
William?
I can try to set it up, but I'm not sure about the calculations.
I mean, that's what we do. We do it together and we figure out where the problem is.
Okay, so you're going to end up with negative Laplace to the -1, or TFT as a
Mm-hmm.
negative Laplace to the -1, d over dx, cotangent to the negative first of 2s.
Yeah, let me put it there. We just split.
Minus the natural log of s
Mm-hmm.
minus 1, or s plus 1, my bad.
Mm-hmm. And then
Yeah, and then after that, I'm lost.
you got a problem with cotangent minus 1 derivative. So
Yes, sir.
how do we find the derivative of cotangent? Anyone wants to help? Ethan?
I just have like kind of the cheat of it memorized, where the derivative of arc cotangent x is, I believe it's 1 over 1 plus x squared.
No, that's for tangent minus 1.
Isn't it negative?
That's negative, right? So the derivative of cotangent is going to be negative. And here it's 2s. And then the derivative of 2s is?
It's just s.
Yes. No, not s, but
2.
2. 2. And then here you got minus the derivative of this is 1 over s plus 1, right? Everybody agrees with that? Do we all agree with this?
I agree with it.
Okay. Now let me see this here because there are problems. How do we find the derivative of with respect to x of cotangent minus 1 of x? First of all, what's the derivative of cotangent of x? How do we find the derivative of cotangent of x? I want to walk backwards to show you where this comes from. So I want you to help me here. So what's the derivative of cotangent?
Isn't it negative cosecant squared of x?
Negative 1 over sine square x, right? Which is technically negative 1 plus cotangent square of x, because 1 plus cotangent square of x is equal to this 1 over sine square, right? Everybody agrees with that? Cotangent is cosine divided by sine. So when you square that and add 1 to it, you get cosine square plus sine square over sine square, and cosine square plus sine square equal 1. That's why it's 1 over sine square. And why do I turn this into 1 plus cotangent square? Because it's important in establishing what the derivative of cotangent is equal to. There's this formula that the derivative of the inverse of a function is 1 over f prime of f minus 1 of x. Have you seen this before? Are we together? Hello?
Yeah,
I've
we're
personally
here.
never seen it.
I've also never seen this before.
That comes from the chain rule. This formula comes from the chain rule because the inverse function is defined as the function such that f composed with f minus 1 of x equals x. That's the definition of the inverse function. And if you take the derivative on both sides, the derivative of x is 1. And the derivative on the left, you use chain rule, it's going to give you f minus 1 prime of x as the inside function times the derivative of the outside function as the inside function. And then you divide that, you get f minus 1 prime of x equals 1 over this. And technically, this is the formula that is used always to identify the derivative of the inverse function when we don't have a closed form for it and we're having trouble. You do the same thing to figure that actually the derivative of arctangent x is 1 over 1 plus x squared. We use this to prove it. And we use the same formula to prove for cotangent. Now that we know that the derivative of cotangent is this, so if I take this here, the derivative of cotangent is that, and I apply this formula, derivative of cotangent applied to inverse cotangent. So that's going to be cotangent of x, cotangent prime of cotangent minus 1 of x is equal, and the derivative of cotangent is that minus 1 plus cotangent squared of whatever is in here, cotangent minus 1 of x. And cotangent of cotangent minus 1, by definition, this is it, equals what is inside. So this is minus 1 plus x squared. And so this is the denominator of the derivative. And that leads to cotangent minus 1 of x equals minus 1 over this. That's it. That's why it is true. Same thing works for tangent, and that's why this formula is okay. And then you take the derivative of what is inside, it's 2. Then you go to the next step. Minus and minus, all the minus inside there turns into plus. So you got, and here, because you got a 2 here, you gotta divide by 2 as well. So it's gonna be 1/4 that you can remove from there. And this is gonna be 1/2 inverse Laplace transform of 1 over 1/4 plus s squared plus inverse Laplace transform of 1 over s plus 1. Now you tell me, what is the inverse Laplace transform of this?
Isn't it sine 1/2 t?
That's sine 1/2 t, but and the second one,
I got e to the negative t.
e to negative t, that's what it is. And so that's t f of t equals
And
that.
then the sine 1t, isn't that multiplied by a half?
But the half goes up here to half sine.
The half in front of the inverse Laplace transform that you factored out.
I say that half needs to get in here for this thing to be sine 1/2 t.
Oh, okay. My bad.
Yeah, that's one too. We're fine. So are we good? Did we mess up something somewhere? If not, then we are going to get f of t equals 1 over t. All right, questions?
Is that e to the t or e to the negative t in that final answer?
T, it's 1 over s plus 1. So, okay. So when is our new next test? Anyone remembers?
Isn't it a week from next Thursday? So I guess 2 weeks from today.
I wish I knew.
Because we have homework due, not this coming Sunday, but the next. So our test would be
On
not
the
next Thursday, but the next.
15th, right? The 15th, 2 weeks. Okay, so, right, let me give you more examples that you can try to answer here for me. And the question here is evaluate without computing the integral. And that goes back to what we just did in general for the integral, okay? So what is the Laplace transform of integral from 0 to t e to the tau cosine of tau d tau? Can anyone just tell me quickly what this guy is about? That's one of the problems we solved already today. Mr. Brown,
Not sure.
Jimmy,
Isn't it 1 over s Laplace of cosine t, e to the t?
that's correct, sir. Thank you. And then how do we compute that one? Again, Macy.
You change the t to it's using the first rule. It's like when you change s to like s minus.
That's what it is. Anytime you see E, you know it's translation theorem, right?
Yeah.
Mhm. So what goes here?
The Laplace transform, it would be the Laplace transform of cosine t, and then you would be changing s to s minus 1 because that's the coefficient for the e to the t, right?
That's right. And so that is, and what's Laplace of cosine?
S over s squared plus 1.
That's it. And this is 1 over s minus 1 over s minus 1 squared plus 1, which is nothing but s minus 1 over s times s squared minus 2s plus 2. Questions? Any questions? All right, if you have no questions, then we have 10 minutes left, and I'm going to give you one application to solve. Let's say I want you to solve f of t plus integral from 0 to t f of tau d tau equals 1. I want you to solve this equation. Solve for f of t. As in the example that we did last time, you need to apply the Laplace transform to both sides of the equation and solve for the Laplace transform of f of t. What you get when you apply the Laplace transform to both sides? Let's go together, otherwise we will not succeed. What you get applying Laplace transform to both sides? First line. And go with me, Preston.
Well, on the right side, you'll get 1 over s.
I'm interested now in the left.
It would just be Laplace of f of t, right?
Close,
Laplace of the integral,
which is equal to
f of t, or
the formula for that was given today.
Isn't it 1 over s Laplace transform of f of t?
All right, that's what you get. And then you solve for the Laplace transform of f of t. So if the Laplace transform of f of t is 1 over s plus 1, then what is the Laplace transform of what is f of t?
E to the negative t.
That's it. That's how you solve the problem. One step. Any other questions? As of now, if you do follow all the instructions that are given here, you shall be able to solve almost all the problems that involve Laplace transforms, except for the convolution theorem that I'll give you next time. That's it. The rest will just be repeating over and over and over the same things. If you have any questions, you feel free to ask them. If you don't, then I'll be happy to see you next time if I'm still alive.